Okay, welcome back. So the first question we asked at the end of the last segment was, can you ever have a system that has unsteady mass flow and steady energy transfer? And the answer is no, never. Think about it mathematically, just in terms of the governing equations. If you have an unsteady mass flow term, what you're saying is you need to include this term explicitly, right? This would be the term from the conservation of mass. And now the second part of that statement said there's steady energy transfer. So that's saying that the change in the energy associated with the control volume is zero. You can't possibly have these two assumptions occur at the same time. If there's mass in the control volume, it has energy associated with it. And if that mass transfer is unsteady, then the energy transfer has to be unsteady. And the second question is very similar. When can you have only flow into a system and no flow out? The only way you can have mass transfer in one direction is if you retain the unsteady flow terms, that there's mass accumulating in the system. The mirror image to this is what system can actually have only flow out? Well, that would be essentially depleting a tank or something, that's sort of the example. That only happens if you deplete the mass in the control volume. So again, my example here is if you have only flow in, it's just like when you inflate a balloon. Your conservation of mass expression would look like this. Okay, so that's perfectly allowed, but you have to have this term be non-zero. Okay, and we will cover some unsteady equations or unsteady examples. They're pretty tough, and for reasons that we can hint at right here. So imagine if you wanted to solve this equation. Imagine if you want to do some analysis here. Well, you would want to integrate this expression on both sides. This is the easiest integral we could ever do. This could be easy if we make some very strong, bold assumptions. In particular, what happens to the mass flow rate as a function of time. So if you think about our balloon example, it may be a little bit harder to conceptualize blowing up a balloon, but let's imagine deflating a balloon. The flow rate is not steady as a function of time. In particular, as the pressure in the balloon decreases, as the balloon deflates, the flow rate decreases as a function of time. So this term here, we would need to understand how does that term vary as a function of time in order for us to evaluate that integral. So these can be tricky systems if we can't invoke bold assumptions like some sort of time dependence for that mass flow rate. Okay, so we're starting to see the tip of the iceberg on how our systems that we consider very simple things, inflating a balloon, can be really complicated in terms of the actual analysis. So we're going to do some examples. It's the best way for you to become skilled at using these state relations and the conservation relations. Okay, so let's start with water compressed. This is an example of compressing water. And we're going to start from an initial state where we have saturated water vapor. So immediately you should be thinking, aha, that has a quality of 1. And I have a pressure. So I have quality and pressure. My system is fully defined in terms of being able to find the thermodynamic properties. I'm going to compress it, so we know the pressure should increase, which indeed it does, to a high pressure of 1 megapascal and a temperature of 250 degrees. The water is actually cooled during this compression process, and we are given that cooling, the specific energy of the cooling, not a heat transfer rate. We're given the specific heat transfer. So again, the units and the language here are hopefully cueing you to some very specific interpretations. For example, this would tell me that I have a lowercase q. I have the heat transfer normalized per unit mass. Okay, so we're asked to analyze this process. We are trying to understand, does it require work or does it produce work? We don't know. And evaluate the specific work of the process. So again, specific work, I'll try and make that a lowercase w so you can see it here, is the total work divided by the mass in the system. And then we're going to sketch the process on a PV diagram. When you do any analysis, you should use these steps, these procedures. The very first thing you need to do is define the system. Fine. We're going to go through and define the system. We know we're compressing by some mechanism. We don't necessarily know how. Water. Okay, so we're going to place that water into some arbitrary volume here, my little piston here. We know that the water is cooled during this process, so we know that we have some heat transfer out of the system. To be more specific, we know that we have a specific heat transfer out of the system. We're going to guess that the work is into the system because we need to make an assumption. So we are going to guess that there's work in, and we know that work in is going to have a negative sign associated with it. So if we get an answer that is negative, then we know our guess was correct. Okay? We are going to neglect kinetic and potential energy effects because in our little conceptual system here as a piston, we're not going to have a whole lot of changes in kinetic and potential energy. Okay. So we define the system and we look at the system, and again, our tools are going to be the conservation of mass and the conservation of energy as shown here, and the state relations. But we tend to invoke state relations only on an as-needed basis. Okay, so this is a closed system. We don't see any mass crossing the system boundary, and so we know that the conservation of mass for this system is really simplified. The mass is a constant. And I'll redraw my little figure here of my piston and my control surface. Okay. And we're going to look at the conservation of energy, and again, start with the conservation of energy in its most general form, which says that all changes in energy within the control mass have to be balanced by the heat transfer and the work transfer that occur on that mass. And again, we're given this information. We're going to neglect kinetic and potential energy effects, so the left-hand side of this expression becomes this. And what we want to do is we have information that's on a per mass basis. We know the mass is constant. So let's go ahead and simplify this expression by dividing it in the left-hand side and right-hand side by the mass in the system. So what we get is the U at the final state, the specific internal energy at the final state minus the specific internal energy at the initial state is simply given by this expression here. Okay, so we need to know the state. So what do we know? What don't we know? Okay. We're given the heat transfer. We're asked to find the work transfer. We need to have information from the initial state and the final state. Do we have enough information in order for us to fully define the initial state and the final state? So that's step 3. Find any missing or required state information. Well, we go and we look at what we know about state 1. At the initial state, at 1, we know the quality is equal to 1, and we know that the pressure is equal to 200 kPa. So that system is completely defined. That state is completely defined. At state 2, we're told that we have a temperature of 250 degrees C, and we have a pressure of 1 megapascal. We don't know where we are with respect to the saturation region with this information yet. That's actually a pretty advanced skill, is to be able to take your state information, specifically pressure and temperature, because those are the only independent parameters. Those are the only variables that we're concerned about, whether or not they're independent or dependent based on state. So it's only those two that we know are dependent when we're in the saturation region. So we look at these, and you'd have to go to your tables or your online your worksheets and things like that, and you'd have to be able to identify what state am I in. Am I in the subcooled liquid? Am I in the saturation region? Or am I in the superheat region? For this problem, I want to simplify the process a little. These state conditions are actually outside the range of what our online calculator will provide. without buying the official full version. So these conditions, sure, they're well known. There are lots of steam table data sets out there that you could look up the information for these two states. But our online calculator can't do it. So what I want to do is tell you they're fully defined. This is in fact in the second state, the final state is in fact in the superheat region. And I'm going to give you the internal energy for each of these states, knowing that, again, part of your learning process is you're going to have to become familiar with steam tables, whether they're tabulated versions or whether they're online calculators, and understand how to use them and interpret the information. So we will come back to looking at tabulated information in this class, but for right now I just want to work this example, just saying, hey, look, you can identify that there are two independent intensive properties for these two states, so the states are fully defined. So you would take this information and look up the internal energy, the specific internal energy, and you would get a value of 2,587.9 kilojoules per kilogram for state 1, and for state 2, you would get a value of 2709.9 kilojoules per kilogram. If you have access to a more complete set of steam tables, or if you already have another thermodynamic textbook that has the steam tables listed, tabulated form, you should go ahead and practice looking up this information. If you don't, just assume we'll build that a little bit later, how to use the tables in this class. So again, for right now, practice with that if you can. If not, don't worry, we'll come back to it. Okay, so now we have the internal energy for the final state and the initial state. We can come back to the conservation of energy, and we can solve for the variable we were interested in, which was the work transfer. And so, here, I'll just pop that back on the screen here. So again, here's our governing equation. If we solve for the work transfer on this screen, we can see that what we have is essentially the work transfer comes onto this side, and we end up with, we have plus 2. So this is the equation we're trying to solve. So we go back to take that onto the next screen, or onto our next slide. And what we have is and if you plug in the numerical values, we have 93 kilojoules per kilogram. Remember, that's heat transfer in, so it has to have a negative sign associated with it, because that's our sign convention, heat transfer out. So the water is cooled during the process. So as we substitute in the numerical values from the state parameters and from what the given information was, we need to remember that the water is cooled during this process. So as we take that value for the heat transfer, we have to include that negative sign, because remember, that's our sign convention. Heat transfer out of a system is negative. So we have minus 93 kilojoules per kilogram here, plus 2587.9 minus 2709.9, both in units of kilojoules per kilogram. And everything has the same units, so everything looks nice and consistent. When we punch that in our calculator, and what we get is a value of minus, we can see already, we know it's going to be negative. This term is negative, and this term, the internal energy at the final state, is greater than the internal energy at the initial state. So we know we're going to have a negative term on the work. What does that mean? That means work in is the correct assumption here, because recall back up here, we assumed work in, okay? And so we've learned that to compress this was a saturated vapor at the initial state. So to compress a saturated vapor to 100 of water to 100 megapascals requires that we put work into the system, even if we cool the vapor during that compression process. Okay, so what I want you to think about now, we've gone through this analysis. do you have enough information to determine the total work for the process? We evaluated the specific work, the kilojoules per kilogram, the work per unit mass in the system. Do we have enough information to find the total work? If we do the calculation. If not, tell me what information you need to find the total